All right, tonight what we are going to be talking about are acids and bases and the basics. A lot of this will be representative of the lab that we've already done in class. We're just kind of going a little bit more over it and in depth. All right, so what are some example of acids? Whenever you have a citrus fruit, what they have in it in common is a citric acid in it. And that citric acid is actually what leads to the tartness or sourness. If you've ever been bitten by an ant, like a red ant, what they are doing is they're releasing formic acid, which is a weak acid, into your skin and bloodstream. In fact, when you have a bee sting, what they are doing is they are releasing sulfuric acid into your bloodstream, and that is what you are reacting to is the sulfuric acid, which is approximately 18 molar, which is extremely concentrated for an acid. We also have aspirin, which is a weak acid. You have glycine, which is an amino acid. What's cool about glycine and all these other amino acids is that it's an acid. So it's got this acidic group right here, but it also has an amine group, which is a basic group. So it's both basic and acidic at the same time. Caffeine is a weak base. What is really cool about caffeine, or coffee actually, is coffee in itself is not a base. It is an acid. So even though it has caffeine in it, it still is more acidic that it can counteract that. Sea slugs, if you've ever seen a sea slug, their self-defense is they release sulfuric acid. So if they see something chasing it, they'll release this sulfuric acid, which is the exact same thing as what a bee sting would be. It's extremely dangerous and it can cause some chemical burns going on. All right, lye is actually an example of a base. Most cleaning agents are actually bases. So if I ever ask you about a cleaning agent, you should probably go with that. It's a base. It tends to be. If it has that slippery feeling to it, it is a base. Now, lye is actually sodium hydroxide. It's a soap that's made out of primarily sodium hydroxide. And what they used to use lye for was washing clothing. And what was interesting is you could always tell in the old days a washerwoman from any other woman in those days because their hands would be totally disfigured from constantly putting their hand in lye. Because lye is a strong base, sodium hydroxide is a strong base, and it can cause chemical burns on your skin. So they would always have these disfigured hands from constantly putting their hand in that lye. Liquid soap tends to have potassium hydroxide in it, and that's what makes it that slippery feeling. All right, so there's also another one, which is an antacid. What is an antacid? It tries to counteract your acidic components. When do you use it? You use an antacid when you have an upset stomach, so you have too much acid in your stomach. So what you do is you add a base to it to try to counteract that acidic nature of it. The one that we primarily use in the US is milk of magnesia. Milk of magnesia is magnesium hydroxide, which is a base. So when you ingest this base, what you're doing is you're trying to counteract that acidic part of that of the too much in your stomach. All right, here are some characteristics of acids that you're 100% going to need to memorize. On your test, you're going to have a different section where it says is it an acidic property, a basic, or both, or neither property. So the first one is that acids react with metals to produce hydrogen gas. Why does that work that way? Well, if I have HCl and I'm reacting with magnesium, what is going to happen is that magnesium is going to kick out that hydrogen and it's going to make magnesium chloride, but the other product is going to be H2, which is that hydrogen gas. So whenever you react an acid with a metal, it will produce that hydrogen gas. Same thing is that when you react with a carbonate, it will always produce CO2 as a gas. It can conduct electricity. Why can it conduct electricity? Well, anything that ionizes in water, meaning breaks up and forms these charges, can conduct electricity. And if you look at like HCl, what happens in water is it totally dissociates into H plus and Cl minus. And so because it has these charges, it now can conduct electricity and the electrons can flow from one element to another. It reacts with bases to form water and salt. So if I have HCl reacting with NaOH, okay, this is my acid, this is my base. Okay, how do you identify an acid? It starts with an H. How do you identify a base? In this case, it'll end in an OH. What will happen is this is a basic double replacement, so it'll be making an HOH plus NaCl. Now, the water is always formed of H2O and your salt is NaCl. It could be any other salt though, okay? As long as it's that ionic compound, it is a salt. And these are known as a neutralization reaction. Why? Because neutralization is talking about its pH, and the pH of this one is going to be 7. So therefore you are neutralizing it, whereas these guys, their pHs are not at 7. So when you react an acid with a base, you form a neutral substance. So it's more specific than just saying double replacement. It's saying it's a neutralization reaction, which you do need to know. As you guys probably note, it can burn your skin. So it can cause these chemical burns. It tastes sour or tart. It can corrode metals. That's because it reacts with these metals. It has a pH less than 7, and it can turn litmus paper to red. So if it is red, it's an acid. That's just one way to remember it. And you will have to memorize all of these different characteristics for the test. Bases, on the other hand, feel slippery, so think of that slimy soap, and that's what a base is. It also reacts with acids, duh, to form water and salt. Once again, this is called a neutralization reaction. It can turn litmus paper blue. This should be up here because when you have to memorize these different colors for these indicators, which we'll talk about in a little bit, but a lot of times these indicators turn blue. So if they're blue, they tend to be basic or of a blue property. So purples, they tend to be more of the basic nature. It's a general trend. It definitely does not work every single time though. But if you're at a last resort, go with that. If it's blue, it's going to be a base. It can produce electricity. Why? Because once again, it can ionize in water. So when I put NaOH in water, which is the classic base, you get Na plus and OH minus ions. So once again, it has those charges that can flow from back and forth. It too can burn your skin. As I was talking about with lye, with the washerwomen, it was doing chemical burns on their skin. So it absolutely is just as dangerous as an acid burn, is just as dangerous as a basic burn. It tastes bitter and chalky, and it has a pH greater than 7. So what is this pH scale? The pH scale is an expression, it's a different way to convert the concentration of either your for pH, it's the power of hydrogen. So what it's doing is it's converting this concentration of H plus and it's converting it into a basic 0 through 14 scale of pHs. Okay, so it goes from like 0 to 14. Sometimes you can have a little bit of a negative. It doesn't go past -1 that I know of, but generally speaking, it's like a 1 to 14 or a 0 to 14 scale. And what it does is it just converts the concentration of how many H pluses, so hydronium ions you have in solution, and it converts it into a numeric scale. And we'll talk about how to do that calculation-wise in another video. All right, but what you need to note is when you change this pH scale or change the hydronium concentration, which is that H plus, which represents its molarity, into and convert it into your pH. Anything that's under 7 is an acid, anything that's at 7 is neutral, and anything that is over 7 is a base. Okay, the pH scale is based on the logarithmic scale. So any change in number will be a change of 10-fold in concentration. Once again, I don't expect you right now to understand the conversions between the H plus and the pH scale. We'll get into that in another video. What I do want you to understand that a change of 1 in pH, so meaning a change if I go from a pH of 2 to a pH of 3, I am actually changing it 10 times more or less in concentration. So a pH of 2, which is more acidic, the lower the number, the more acidic, the higher the number, the more basic. A pH of 2 is 10 times more acidic than an acid with a pH of 3. A pH of 2 is 100 times more acidic than a pH of 4. And a pH of 1 is 10,000 times more acidic than a pH of 5. Okay, if I wanted to reverse it, a pH of 5 is 10,000 times less acidic or more basic than a pH of 1. How do you do this? All you have to do is take the difference between the two pH numbers and make that to the 10 to the power of. So 3 minus 2 equals 1, so it's going to be 10 to the power of 1. 4 minus 2 equals 2, so it'd be 10 to the power of 2, which equals 100. So that's how many times different it is. All right? Strength of acids and bases. So there are the strength of an acid and base, we do have something called strong acids and strong bases. And it's really, really, really important that you understand the difference between a strong acid and a weak acid, or a strong base and a weak base. The more readily an acid or base dissociates, the stronger the acid or base is considered. Strong acid, we can say completely dissociate. Weak acid only dissociate a little. Okay, so what does that mean pictorially or graphically? So before I have a solution, okay, I have a strong acid, and we could even say this is a weak, this should be weak acid. Oh, I guess it's saying whatever. This is just showing that it's a different one. Anyway, so this is a strong acid. What happens is when we dissociate it, meaning you put it into water, what happens is it completely dissociates. So the concentration of my solution before is the same as the concentration of my H plus and the same concentration as my other anion. So like for HCl, let's say I had 3 molar HCl. Okay, and it completely dissociates. That means my H plus is 3 molar, and that means my Cl minus would be a 3 molar concentration. Notice in solution, it completely separates. So strong acid completely separates from one another. So the H is no longer attached to the other part of the formula. Whereas a weak acid, what happens is it doesn't completely dissociate. So if I start with a 3 molar, and I put it into solution, now I end up with, let's say, a 2 molar, and I only have, as far as the H plus goes, I have a 1 molar and I have a 1 molar for my base. Okay, so it doesn't completely do it. So instead of being 3 molar, my H plus concentration is only, let's say, 1 molar. I know graphically this does not show it that way. When you look at it in the pictorial way, if I look at all of my HBs, okay, that have not dissociated, those are, I'm coloring them right now. Notice that I only have like really 1 H and 1 B that have separated. And so that just shows that it's a weaker acid. Why is it weaker? Because it doesn't contribute as much H plus. And by definition, things that contribute H plus are acids. So the more H plus you can give away or donate or whatever, the stronger the acid you are. So considering this versus this, okay, obviously this one can give off more H pluses, so it is going to be considered a stronger acid. All right, so how does one determine the pH? pH is determined by knowing your molarity. And what contributes to the molarity? One is the ability for it to dissociate in water. And I referenced that in the previous slide. But once again, if it can totally dissociate, it's going to be contributing everything it's got towards the molarity of your H plus. Whereas if it's a weak acid, it's not going to be contributing everything. And then straight out the molarity of it if it's in water or outside of water. If you have a higher concentration, even if it's a weak acid, it can do more damage than if, let's say you have a 3 molar of something, and you put of a weak acid, and then you have a 0.0000000000001 molar of a strong acid. Obviously, the 3 molar is probably going to be stronger than that 0.0000000, so on and so forth, 1 molar of the strong acid. All right, there are different ways to test pH. One is through litmus paper, and that we did in a lab. Another is like a pH paper. A lot of you guys will use the pH paper for your pools, so it has a wider range of indicators on it. It can tell you more specifically what the exact pH is. A best way is a pH meter, and literally what it does is you put this little probe, it looks like a thermometer, into a solution, and it literally reads out the pH of that solution. And once again, when it does that, 7 is neutral, less than 7 is acid, and greater than 7 is a base. And then you can use another indicator, such as bromthymol blue is a common one, phenolphthalein, these are the two that you really absolutely need to know. You've got phenyl red, there's tons of different indicators. And then you can also use natural indicators like red cabbage, radishes, blueberries. What's really cool about these natural indicators is that they can actually tell you the pH. So I like the one with blueberries because I've done blueberries a lot. If you have a blueberry, that is very basic. Okay, so it's sweet, that kind of stuff. If it's red, that means it's ripe, but what it is it's actually more acidic than the blue ones. And so it's changing its pH throughout by going from red as ripe to blue as, to blue as ready to eat. So when you eat it, the red ones are very tart. Why? Because it's more acidic. So you can actually look at a lot of berries do that, cabbages, radishes, a lot of these things with colors actually tell you the pHs at that time. So what is an acid-base indicator? What it is it's either a weak acid or weak base, depending on what the indicator is. And the reason what happens is it actually changes colors when you have an undissociated form versus the dissociated form. So basically the undissociated form has these extra H's plus that are surrounded by, that it has surrounding it, or the dissociated form is where the H plus is no longer attached to that indicator. And for whatever reason, it actually shows you a different color. So if I have an indicator of, let's say, bromthiamyl blue, when it has the H plus attached to it, it is going to be blue, whereas when it is not, it is going to be yellow, or vice versa. What is the purpose of these guys? First, I can tell you the pH range of a solution because it'll tell you a color, and from that color you can tell the range that the pH of that solution is, which means that if you know the pH range, you also know the H plus range. They're directly related. So if I know H plus, I can figure out my pH, or if I know my pH, I can figure out my H plus. But what it does not do is tell you what the exact acid you have is. So let's look at a pH indicator chart. So here's one that you guys used, which was phenolphthalein, and you use bromthiamyl blue. So what you can notice about phenolphthalein is that it is always clear. So if I put it in a solution and trying to test whether it's acidic or basic, it will be clear until it gets to about, let's say, 8.0. Between 8 and 10, it is going to be starting to change to a pale pink, and then after 10, it is a very dark pink. Okay, so let's say I put a drop of this phenolphthalein into a solution and it turns this bright pink. What I can tell you is that its pH is between 10 and 14. I can't tell you exactly what the pH is, but I can tell you a range. Same thing with the bromthiamyl blue. The bromthiamyl blue can be, it is a yellow before, so it's about 6, and it converts and changes between the pHs of 6 and it's about 8, but it's less, it's about 7.5. And then after that, from 7.5 on, it is blue. So once you know if blue, you know that the range is between 7.5 and 14. If I know yellow, I know it's between 0 and 6. And if I know that it's green, it's somewhere between 6 and 7.5-ish. All right, the L's are in yellow, okay? This just shows you, this is just another pH type of way that chart that you need to be able to read. And what it does is it just tells you when the colors changes. So all of these guys only have 2 different colors that you can change from, red to yellow, or yellow to violet, or yellow to blue violet. They only have 2. Some indicators actually have like an additional few other colors. So let's say I'm going to make this one up, bromthiamyl blue. This is totally made up. But let's say here it's blue, and then as you get past, let's say 10, it turns to a purple. So you would see 2 of these guys for like bromthiamyl blue if this was the situation where it has multi-ranges. And you'll see that with universal indicator. Also red cabbage does that too, where it has different pHs. They're smaller, so 0 to 3 it's pink, 3 to 4 it's purple, 4 to 6 it's yellow, so on and so forth. So it can tell you a more specific one, and that's what your pH paper does for your pools. What they do is they insert it in there. They insert it with all of these different indicators, like a combination of all these, and by putting it in there, it can tell you exactly what pH range you're talking about, because it's got these little more narrow color schemes. So this would be your pink, this would be your red, this would be your purple, so you can know exactly what your pH is, or a closer range. All right, hopefully you kind of have a basic understanding of the characteristics of an acid and a base. Once again, really, really important. Understand that an acid is defined as things that give away H plus in water, and a base is things that give away OH minus, or hydroxide ions in water. All right, have a great evening.